Yes, it's Salah Nasri here, and yes, I have a special announcement. The game of chip has just hit 20,000 orders on Amazon. Thank you to everyone who placed the order. The book was just released in December, so I'm very, very grateful and surprised to date. If you are someone who is intrigued, curious about how the semiconductor ecosystem works from beginning to where we are right now, this book was written with you in mind. So order it, read it, and it is pretty much a handbook of the whole ecosystem. In the meantime, enjoy the next episode and don't forget to hit that subscribe button.
The Bitcoin, which is an elliptic curve code, is like the easiest thing to break that we know of. I hope that my field just doesn't break things.
Yeah, you've made the case that quantum's future depends on semiconductor-grade fab discipline. What specifically do you need from the semiconductor industry in the next 5 years that you are not getting today?
We want a yield to be 99.99%, so that if we build a 10 or 20,000 qubit wafer scale, then maybe one drops out. And in semiconductor manufacturing, it's either zero or unacceptable, right? People have built chips, but it's all been very, I would say, I call artisanal, to be polite. This is, for me, it is absolutely essential. We will not be able to build a quantum computer in a practical, cost-effective way until we use this technology.
Our guest today is Dr. John Martinis, CTO of Qolab.
He has researched superconducting qubits since the mid-1980s and led Google's quantum effort from 2014 to 2020, culminating in the 2019 supremacy experiment. London Prize laureate, Bell Prize laureate, and in 2025, Nobel laureate in physics.
Today, he is staking his startup on a single thesis, that quantum will not scale until it borrows the semiconductor industry's manufacturing discipline.
The semiconductor industry is pretty horizontal,
right,
where people are doing different segments and adding their technology into it. The quantum computing is actually pretty vertical at this point. What happens in quantum computing is people say, oh, I have this magic qubit thing, and then, you give us money and we'll build a quantum computer in a short amount of time. These materials, like silicon dioxide, which is used all the time, it's super lossy. So we end up having to build our chips without using any amorphous insulators like silicon dioxide. Google, for example, the latest chips, they have dropouts, 3-4 dropouts in the chip. How are you going to make a 1,000,000 qubit quantum computer? So what we plan to do is wafer scale, 300 millimeter wafer or so, and that's about 20,000 qubits.
And then the Nobel call came.
With the Nobel Prize, I think people can, trust our opinion a little bit more. That has made it easier. How you might be able to make a smaller quantum computer and break elliptic code. And also there's a Google paper on breaking internet security.
Hello, and welcome back to the Semiconductor Leadership Podcast. I'm your host, Salah Nasri, and yes, whether you are a veteran or someone who's curious about semiconductor manufacturing, this is your podcast. Today, it is with great pleasure to welcome Dr. John Martinis, CTO of Qolab. John Martinis has researched superconducting qubits since the mid-1980s. From 2014 to 2020, he worked at Google to build a useful quantum computer, culminating in a quantum supremacy experiment in 2019. He was awarded the London Prize in 2014 and the John Stuart Bell Prize in 2021. In 2023, he co-founded the startup Qolab to build a useful quantum computer, and most especially, he was awarded the Nobel Prize in 2025. Ladies and gentlemen, please welcome Dr. John Martinis. Dr. John Martinis, thank you for joining us today.
That was a spectacular introduction.
Oh yeah, that's my pleasure. You deserve it. John, I mean, I think the best thing for me to kind of relate to, first of all, it's an honor to have you here. And, I've always been fond of professors, right? I've always been a fond of, especially funny ones as well. I want you to, I know you get this question asked to you before, but, for our audience, which is a semiconductor community, that ranges from engineers to the VPs to the investors, even ministers of states are listening to this podcast. I want them to know, or if you can share with us that moment when you heard about that you got the Nobel Prize.
Well, okay. When they announce it and they make the call, it's about 2 a.m, the West Coast. Okay, and I was fast asleep. The phone's in the way the other side of the house, so I never would have heard the phone call. But my wife happened to be up really late. She does that every once in a while. She'll see, here's this phone call, and calls, and it's like, oh, I'll get it in the morning. That's not important. So she didn't answer, about that. But she went to check her email before she went to sleep, which is a bad idea, of course. And then there was all these messages about congratulations to my wife. Well, okay. So she found out about it, and but it was like 2:30 in the morning or something, and she knows I need my sleep because the day after you get announced, it's like crazy. So she would wake me up. So then somehow the AP press, the Associated Press, called or got in touch with her, and they wanted to come over and interview me in the morning. At 6 o'clock in the morning. They actually wanted to wake me up and tell me, but my wife said, no, you're not going to wake him up. So I found out because my wife came in and she, tapped me on the shoulder and said, oh, there's going to be some press here at, 6 o'clock. And press is like, oh, this is Nobel week. Because you kind of know about it, but I just forgot about it. I was so busy and I didn't tell my wife. So, but, I couldn't believe it. So I opened up my computer and looked at the announcement, and there I was. So that's how I knew for sure. Yeah. And so, I got ready for the day. But I just remember the moment. It's just this amazing moment where, you're honored in this way. And, and that kind of changes your life. But I would say, in terms of being a scientist, it's doing the research, which is really exciting and fun. And then you write it up and then you communicate that and answer questions. That's what's exciting about doing science. And I've got to do that over and over in my career. And if you're lucky, okay, I feel very, very fortunate that we happened to do an early experiment and, was so awarded. And that many other people in the field work hard to invent it so that, a quantum computer was possible to build because of the work of many other people in the field.
Thanks for everyone in the world, right? Yeah, it's the work of many others, and we leverage upon that foundation, right? So I want to put a quick in for the people watching to understand who is Dr. John Martinis. So I'm going to ask you some rapid fire questions.
Okay.
You ready?
Okay.
Superconducting qubits since the mid-1980s. What still surprises you about it?
Well, the basic question was, quantum mechanics is the physics of the small, how light, how electrons, how atoms and molecules work. And the idea about there is that maybe you would see quantum mechanics of macroscopic objects. So in our particular case, it's a electrical circuit about a centimeter across. You could look at the circuit with your eye, and it turns out that this macroscopic object electrical circuit can obey quantum mechanics too, in the standard way that we do that. And that was just a new idea at the time. There were some fundamental physics reasons to believe why it's good to be tested. But, it's just showing that the quantum world is beyond just the physics of the small. It's just, it can be observed in many other things. And that's what's been interesting over the years is people have continued this idea and look for quantum effects in many different systems and open that up.
Academia or industry, which is a tough one, Dr. John Martinis. Which brings out the best science in you?
What brings
academia or industry?
Well, they bring out both. Both bring out, but in different ways.
Okay.
Now, I would say for academia, in my role as a professor, having a goal was always really useful for me, because if you have a goal, in this case, building a quantum computer, I know what fundamental questions to ask.
Right.
And I think other people are better at just exploring all the possible ideas out there. So, but in academia, it always did that. So even when I was doing other things with quantum computing, I was building instrumentation. What experiment was to count electrons from an electrical standard? And then again, we have an instrument in mind, and then I could figure out what questions to ask. So for me, kind of the technology and instrumentation and building something is very much connected to, doing academic physics and asking the right questions.
So this one's actually quite an interesting, the next question, because I'm new to the game in quantum, and we just hosted the Quantum Computing Infra Summit here at the ISIG Quantum Computing Infra Summit, where we had the honor to have you as a keynote. What is one book every quantum newbie should read?
That's a good question, and unfortunately, I don't have an answer. Because, I've been in this so long that I do that. What I try to do is present quantum information in a way that engineers can understand, or computer scientists that are outside the field. So I want to explain quantum computer without using the word Hamiltonian, right? Which is a physics word that you start describing your quantum system with. But the problem is you never use the Hamiltonian in engineering disciplines. So what I do, and you can see some of my summer school lectures, you can find them online. I try to describe how a quantum computer works, but in an engineering language. Now, I imagine I should write a book. I have all the material. I'm just too busy. But, the lectures are out there. You can look them up and see what I have to say. But it tries to explain it in a way that other people can understand. Because I think it's important to have the deep physics understanding, but also to explain it so that, engineers, especially people who are used to doing circuits, how, that they can understand it too.
All right. And so what would be then one book that you would say is your favorite book on quantum computing?
Oh my goodness.
Just one.
That's a good question. I haven't answered that question before. So yeah, that's kind of hard to answer. Gosh, yeah. What?
I'll put you in.
Well, I'm just gonna say something that affected me as a student, as I love the Feynman lectures on physics. And of course, he talks about quantum and the like. Now, I think you generally need to read the other physics books to kind of understand it. But I really like how Feynman kind of explains physics in a kind of a different way that kind of makes it a little bit easier to understand, or tries to simplify the physics in a way that you can get the core ideas. And I would say that those books, the series of 3 lectures, have greatly influenced my career, so that I tried to give my talks and the like in a way that people can understand it in this way. So that was I think the one series of books that influenced me a lot.
Appreciate it. Quantum supremacy in 2019. What did you feel in the moment the result came in?
So it was a great relief because I had been talking about this for a couple years and how are we going to do it. And I think a lot of people were skeptical whether you could get, at the time, would be a very complex experiment, and whether the experiment would work and whether, you can calibrate it, even if there was other dirt physics that, would cause it not to work. So the team worked very hard on it. There's a lot of people, many, many hours, inventing things all the way, really amazing. And I was there, trying to help as I could. But, I had been talking about this publicly. So it was, I like to say, a relief that it worked, and that the other thing is that the Google quantum effort started pretty small, and it turned out there were a lot of executives who were very dubious that, why were we doing quantum? Why would this little physics experiment be more powerful than our big data centers? Isn't this too basic of science? So I would never told, anyone in the group this, but I was aware that, this was a little bit of a difficult project for them. And the quantum supremacy was kind of promised as a gateway that if we did this and showed that a quantum computer can be powerful, then, Google put more funding into it, which they did, which was really good. So I was aware that there's a little bit of a high stakes for us to get that to work.
Marvelous. The app on your phone that you couldn't live without.
Right.
What would it be? What would be the app on your phone that you could not live without?
Oh my goodness. Right now, it's for my Tesla. We just got a new Tesla with full self-driving. Okay. And that is so fascinating to watch this it's a robot, right? This robot work. Okay. And how does it work and how does it drive? And, it's much safer than I am. Okay. So that I find that interesting. It calms down my drive. But the other thing is, I'm getting older. My wife has chronic fatigue, and she'll go out shopping or something, and then she'll get tired. And if she has to drive home tired, that's a lot more dangerous. So for us, it's actually a huge safety feature to have this truck. But it's funny because the car, it's a robot. It's kind of like our pet. We treat it like our pet. It's like, Dad, why you didn't turn there? So it's fine. We got a lot of fun with that.
What about the iPhone app that you? Oh no, it's just popped out. Yeah. Hello. Oh, yeah. The iPhone app here that you couldn't live without. What would it be?
Oh, the app I can't. What I don't know. I guess Google Chrome, with YouTube. I enjoy YouTube. I enjoy learning about different things on YouTube. Right. That's the one thing I do all the time. I don't do much social media. I find that kind of psychologically difficult. I like talking and having this kind of interaction, but seeing people's comments or whatever, that just
it's not your cup of tea.
Yeah, it's not my cup of tea.
Coffee or something stronger the night before you submitted the supremacy paper?
Oh my goodness. What did we do? There were some difficult moments around that time. So I don't remember doing anything like that.
I think that says it all, the answer.
Yeah. The Google management changed around that time.
Yes.
And I kind of got demoted during that time. So it was beautiful. I love the paper. It's a great paper. But at the same time, professionally, me at Google, I was kind of getting lost there. So it was kind of a hard time, in fact.
In one word, how would your Qolab colleagues describe your leadership style?
Okay. My leadership style, how would they describe me? That's kind of harder. What I try to do, and I think they would say that, is to make sure we're very honest about what we're measuring. We have a Qolab values, and one of them is called metrology, not mythology.
Nice.
And what happens is you have ideas on how your systems work, and you do experiments, but a lot of times these ideas aren't tested, or they aren't really the most profound, best ideas you could have. And we have to really make sure we're always measuring things very carefully and testing it against all the different models to make sure it's right. And in particular, what happens in our field is that people report what we call the hero device, the dice that's really good, a long coherence time. I mean, it's probably like making a transistor circuit and testing 1,000 chips and finding the one that has the fastest clock speed. Okay, and then publishing that as that's how fast, and we all know that doesn't make sense at all, right?
Yes.
It's like when is it all to work? What's the average? So I would say I think we really try to focus on doing measurements really, really carefully.
Biggest
And I will ask questions all the time.
That's the
about that. And maybe they get annoyed at that because I've maybe it's like a little bit challenging. Why do we know that? But you have to do that to make sure you're really making the right conclusions.
The biggest myth about what quantum supremacy actually proved.
The biggest myth.
Yes.
That's an interesting question. I think the biggest myth. Okay, I'll answer it in a strange way. The biggest myth is people hated the word supremacy. So it's quantum advantage that they want to talk about. So why was this? Well, it has to do with politics. And no surprise, Trump as president at the time. And, the whole world's supremacy is kind of tied to white supremacy, which, I understand that people, don't like. But it's just kind of this weird thing that you're playing word games, and that. So what was nice is it was a little bit controversial at the time or whatever. And actually, there was a Wall Street Journal editorial about the word achieving quantum wokeness.
Wow.
Because of this controversy about the word supremacy. So that was the best part of that whole controversy, of that whole myth.
Yes.
And I really appreciate they wrote, to get a Wall Street Journal editorial about the title of your science paper. That's that's pretty out there.
Yeah. Dr. John Martinis, if you weren't in quantum physics, what field would you be in?
If I weren't in quantum physics.
Correct.
I think right now the world of astrophysics, astronomy is very interesting. I'm an experimentalist, and they're building some really amazing detectors. In fact, using some quantum physics kind of ideas. I was involved in this in the mid-1990s, and building these detectors, very sensitive detectors, I think was very fascinating, and I would love to contribute that. Again, it's kind of instrumentation, but with these kind of new instrumentation, you can then do new measurements in astrophysics. And that's, for example, someone's doing that UC Santa Barbara, helping find exoplanets, using these advanced detectors. And it's a beautiful physics and beautiful experimental physics, what they're doing.
What's one thing 4 decades of qubit research taught you that you couldn't have learned in less time?
God, these are such good questions. Thank you. I like that. I would say how persistence in a technology is important. That it took, 4 decades to figure out everything we had to figure out, and that it's going to take more time even to perfect it and refine it and make it more manufacturable. And it just takes a long time to develop technology and, so that you can use it practically.
Thank you. That was the rapid fire round. Okay, I hope we're just getting warmed up here. Right, so John, we're getting way.
I didn't know that was rapid fire.
It was a bit longer the answers, but yeah, okay. Now we get a good understanding. Let's get into it. Yeah, you've made the case that quantum's future depends on semiconductor-grade fab discipline.
Right.
And this is something my audience is going to love hearing now.
Right.
What specifically do you need from the semiconductor industry in the next 5 years that you are not getting today?
So what we've done so far is we've worked with one foundry and then also a tool maker to Applied Materials. And we've learned how to work with them and use them. And we know that we just have to continue doing this. We know that the model works and the like. And what we really need is to raise more money.
Yes.
And to get more, maybe corporate support from these entities to really do a serious effort. Because what we've done so far has been good development work, but nothing like the development you do develop a real semiconductor process. But what we've learned so far is that it works. And that we're going to continue. We're making progress. If we had more resources to do all the little things we needed to do to build it, I'm sure we could be successful in it. So we just need to keep doing what we're doing. I'm absolutely certain that we can build these things from the preliminary results we've already been getting.
So many of our members sit in the supply chain that kind of you're depending on, whether it's the material, packaging, deposition, wet processes. Could you name one tooling or materials bottleneck that you believe the industry has not yet understood is a quantum problem?
So I'll answer this. I think I'll answer this a little bit different.
Please.
But what we're trying to do is build a quantum computer using wafer-scale integration. And for example, if you look at the company Cerebras, they're making AI chips that are a full wafer.
Right.
Okay, so we want to make our quantum computer chips from a full 300 millimeter wafer. Now, it turns out you need multiple wafers to do all the things you need to do. So building on 300 millimeter wafer, we're going to work on it. There are lots of things we have to do. But in the end, we have to assemble the various wafers, and we're going to have to do that with bump bonding, which the field already knows how to do. But we want to do like full-scale kind of bump bonding, or bump bonding wafers where, we're bonding it over. So we believe this can be done because people are already quite sophisticated in bump bonding, but doing it at a wafer scale, at a large scale, is something that is kind of happening now with all the AI chips, so how they're building it more and more powerfully. So people are developing the technology more, but we have to develop, take that development and use it for our particular case where it's going to be a larger scale bump bonding. So that's the one thing. Now, there's people who already acknowledge they're thinking about it and the like, but I think if people were to contact us, if they have specific ideas or technologies to do that, it could be very helpful.
Interesting. And I want to kind of shift a little bit the discussion into government and policy. Okay. I know you're advising the government,
Right.
U.S. government.
We haven't met yet.
You haven't met yet? When
No.
meeting?
Well, I think there's some other things going on. The lighthouse that they're paying attention to. Okay. And also they've I think the most important thing of that, of course, is AI. It's very transformative. The science part of the White House has already met and dealt with that. So, I'm sure we're going to meet, but yeah, we have to get their attention on science.
Sure.
But you're well aware of that where you live. So you want that to be solved. We're not. So that's all. They're not gonna distract people in Washington. Okay.
No. But I mean, like, imagine in an ideal world, or in a world of peace,
Right.
From a policy design standpoint of view,
Right.
and that's why you're involved.
Right.
In this. If it was, and it could happen, the Quantum Chips Act
Right.
can happen. What would you say a Quantum Chips Act would actually need to fund, at what scale, and over what horizon?
So, I'm generally not connected into Washington politics. I'm in my lab trying to build a quantum computer. That's where my strength is.
Right.
I find it very interesting here. I think my role is I need to go to Washington, be part of this, and then hear what's going on in the government and what they're trying to do. There's been some changes in the U.S. funding that's kind of important and interesting. I mostly want to hear what the policies and what people want to do, what they think they want to do, and then comment on that based on knowledge, because my knowledge right now is minimal. I know that the CHIP Act is going through Congress. I get updates on it. I'm on an email distribution list. I'm glad it's working its way through, because I think that's an important component, kind of on the public sector, especially in science and training. That's important. But
okay, so we can't delve in a little bit deeper. We still need the podcast too, Dr. Jonathis, when you're in there and you've had the discussions. So modern CMOS today is vertically integrated across a $1 trillion industry. Quantum isn't at the moment. What would you say is the earliest point in quantum hardware stack where you think a true merchant ecosystem, independent of fab, independent of tooling, independent of packaging, becomes viable?
Let me answer something to connect to what you just asked. The semiconductor industry is pretty horizontal,
right,
where people are doing different segments and adding their technology into it. The quantum computing is actually pretty vertical at this point. You take Google, where I work. They're trying to do everything. IBM's the same way. Rigetti's the same way. You look at the other modalities. People are trying to build the quantum computer, in-house by themselves. It's very vertical.
Yes.
This is the way the semiconductor industry was in the 50s, 60s. Think IBM.
Yeah.
Okay. But then in the 70s, 80s, it kind of went horizontal. And I would say Qolab, that's what our realization is that if we really want to manufacture this very precisely, cheaply, and the other, we're probably going to have to go to a more horizontal. So we're working with our fab partners. We're working with, Hewlett Packard Enterprise to make supercomputers. We work with other companies. So this is something called the Quantum Scaling Alliance, where we work with a group of people who are doing it and then collaborate together. We think that in the end, that's the model it's going to be, just because that's what the semiconductor industry, maybe not at first, but we think and especially for us trying to build the quantum hardware, we think by horizontally integrating with people who can fab the wafers, who can think about the packaging, other things we need to do, test and measurement, that's going to be the more effective way to put everything together.
Let's go into. Thank you for sharing that, Dr. John Martinez. Let's go. I want to go a little bit into the technical depth now, because I know the folks on the other side are going to be scratching their heads if I don't go deeper. So, based on the analysis that my team has done, it'll be interesting to understand on your side, Dr. J, is like 2-level defects remain by your own argument, right? The dominant decoherence improvement on paper. The dominant decoherence source on your side. How close is the field to defect density target that actually unlocks scaling? And I'd be also intrigued to hear from your perspective, what measurement convinces you when you actually can be able to see it?
Okay. So this is a complicated issue, but I think I can do that. So what we primarily worry about at this point, just to simplify things, is what we call the coherence time. But think of it as a memory time.
Yes.
When you have dynamic RAM, it only lasts for so long. Okay. So the same thing happens with quantum. You dissipate away your energy. And people have been working hard to use the right materials and designs to do that. There have been some very nice results recently on that, but from a fundamental point of view, I still quite understand it. So we're trying to work with people and figure out exactly what's going on with that, and work on what's the right materials and processing. That's just optimizing some things that people have demonstrated. But the other thing that I really worry about is these called 2-level state defects.
Right.
And what happens is in our amorphous insulators, like let's take up silicon dioxide, you have atoms, because they're randomly bonded. The atoms can kind of have two positions, and they quantum tunnel. They oscillate between those two positions at a microwave frequency, and then they absorb the energy, from our qubit from that. It turns out that these materials, like silicon dioxide, which is used all the time, it's super lossy,
right?
Okay, because of that. So we end up having to build our chips without using any amorphous insulators like silicon dioxide. So imagine building your microprocessor without insulators that you can build up. In this way, silicon's okay. That's an insulator, but that's crystalline. So that makes your fabrication a lot harder, and you have to build it in a very special way to do that. Now that's what we've done. We figured that out. We're still trying to do that better, but the problem is just a little surface oxide on our metals can have this, and then give a problem. So what happens is when you make these complicated processes, like for the quantum supremacy experiment, what happens is you have these 2-level state defects that are at the qubit frequencies, kind of put there random. And then what you have to do is you have to operate your qubit away from those defects. And then you can get it to operate and fine. But those defects move around in time. So that kind of makes it really hard to operate the quantum computer. So things are working well now, but I think it'd be very hard to build a 1,000,000 qubit machine with all this stuff going on. So what we're doing is we're making the junctions in a little bit different way, where we think these 2-level state defects will go down by a factor of 10. And we think if we get that factor of 10, it'll really make everything much, much easier to operate, and you'll be able to scale much better, and you can get it to work. So we actually think, our projection is that's a critical thing we have to understand in order to, scale it up in a reasonable way.
I had one person send me a comment when I put it out saying that, give me a question that you, if you were in my position, what question would you ask to Dr. John Martinez? So He's written it right here for me. I've actually got it highlighted in blue, and I think it'll be angry if I didn't ask it. The surface code's physical to logical overhead is brutal. Right. I mean, that's known. So what he says that, so if you look at the LDPC code, they promise, of course, substantial improvement in general, in documentation. So what specific hardware capability would tip the industry from surface code pragmatism to something that's more default?
Yeah. So what I would like to say is I liked your word saying it's surface code pragmatism, because that's the way I look at it, where, in surface code, you're connecting to the nearest qubit. And when you build a chip, that's very natural to do.
Right.
Now, there are ways to do long-distance communication, and people are working on that, and I think that's possible to do.
Okay.
I think, it'll be good that people will develop that. There may be other ways to do that. We listened to a talk yesterday where people showed a different way to do that, which is good. So, I think all that's possible. Now, the one thing that I caution readers about is that although the LDPC code is claimed to be superior, it's not 100% clear in my mind that it'll actually work, because people are still doing research on that. For example, when you do the surface code, you see errors and you have to decode it.
Right.
You have to say, okay, I did these partial measurements, and then from that I can infer how there was an error and correct it. And it's decoding, and it's hard. And the surface code is really simple decoding. I mean, I could, in my lectures, you can kind of explain how it works and the problems, whereas the LDPC codes are much harder. And people invent codes all the time where, you can't decode it. It's too complicated to decode. So I think it's great people are doing research, but we have to see if they can actually make realistic, fast, decoding things to actually take advantage of it. So in the end, what this leads to is something I call systems engineering. There's more than one metric. I agree, the metric, number of physical qubits to logical qubits, that ratio is important. However, if the metric of whether you can write a software code to actually, decode it, okay, if it's possible, that's an important metric too. Or how long does it take? And it turns out that superconducting qubits are really fast. You want fast qubits. But, if it takes a long time to decode, well, then you can't use it. So again, there's a lot of things people do. So it's great research. Now, the way we're viewing it is, it's great to start with a surface code, you know how to do that. But whatever technology we develop there, if there's these other ideas, you can then, switch your architecture design, just like people design different IC chips based on new architectures. And, once you have the basic technology, it's some work, but you can do that switch.
And combine it. I saw a great slide that you, it was you, it was yourself. I mean, Alan's, your CEO, your colleague Alan.
We talked to Alan a couple of days ago.
Yeah, a couple of days ago. And you presented a slide yesterday. And I wanted to go a little bit deep in terms of the design that Qolab has, which is cool if you pull it off. I hope you pull it off. But when you look at like dilution refrigerators that hit cooling power walls as cubic counts keep growing and growing and growing, is the scaling power, or is the scaling answer actually more fridges in parallel? Or would you say it's more, cryogenic integration? Or is it something that Qolab is doing very unique?
So what we've done is we've proposed an architecture. We've put out a paper on that where, although it's not in the paper because we have to, keep confidential some things. So we've looked at area and power and cryogenics and everything that we think we can do this.
Right.
So we've gone through the calculations, and I know enough about qubits, and I know enough about low temperature physics.
Yes.
By the way, students now are trained in quantum computing, but they're not really getting trained in low temperature physics anymore. So as an old guy who was trained in low temperature physics, I have a specific responsibility to really think about the engineering of all this.
Yeah.
But anyway, we've done the calculations and we think it should work. Now, in particular, we're proposing to use a silicon wafer in order to connect the electronics at 3-4 Kelvin to very low temperatures at 20 millikelvin. And if you look in the literature, silicon wafers have the thermal conductivity of copper, which is this great thermal conductivity. So no one would ever think of doing this. This is the craziest idea. However, if you design that right, you can get it to work. So, that's something we've shown. We've taken the data. We haven't published it yet. But that's a big part of of everything we're doing here. We think that we've analyzed the whole system. We think that this can work. Obviously, I'm experimentalist. I know I have to build it.
Right. I'm looking back at yesterday's presentations, and what was interesting that was kind of shared at the summit was cryogenic CMOS control electronics. That was kind of we had the guys at Intel mentioned it, the Google folks SEEK mentioned it, and it is an area few outside the field appreciate, I would say. How close is it being a real commercial category from your perspective?
Well, we actually did a small experiment with someone from Fermilab where we made a cryogenic CMOS digital to analog converter with the idea that we could then control some of our superconducting electronics with it. And they were able to design it and build it to get it to work first try.
Yes.
It's a pretty complicated circuit, not too amazingly complicated,
Right.
but it exists. People have PDKs. They know how to design it. We would have to move on, iterate on that design. But, people have built these systems, and, we would have to learn how to do that or collaborate with people doing that. But, the real thing here is that for CMOS, you can build chips and yield billions of transistors.
Yeah.
We'd probably need, millions. Okay, but that, if you design it right and do it right, that should be manufacturable. And that's what I find really interesting. The interesting comparison is people are thinking about superconducting digital logic and building it that way. And, again, that's lower power. It's really interesting. But the problem is there's not, commercial things that really use that. People have built chips, but it's all been very, I call artisanal, to be polite, okay? And, you choose the right one and you test it and you get it to work. But we need something that can be manufactured. So I agree. That's why we're thinking about cryogenic CMOS doing it. And our particular design has a very minimal amount of control at the very low temperature with superconducting logic. And we would have a lot of the complexity at 3 Kelvin where you could do cryogenic CMOS, and the power dissipation from that would be okay. So we're trying to, we proposed an architecture that we think matches with what technology can give us. Now, for cryogenic CMOS, we have to start up a project on that. We're talking about doing that to start gaining that in experience. It's not a trivial thing to do at all, but we think it's just a matter of spending the engineering time and partnering with the right people to do that.
For those that are out there, I'm not sure they know much about Qolab, and I think it's very important to mention this, is that what Qolab makes it so unique with our partnership, right, that we have together, is the latching on the semiconductor processes. So Qolab targets wafer-scale manufacturing.
Right.
That's the goal, right? So what is the yield curve you and Alan are willing to accept on a 1,000 qubit die?
Okay, we're willing to, we want a yield to be 99.99%, so that if we build a 10 or 20,000 qubit wafer scale, then maybe one drops out. And, in semiconductor manufacturing, it's either zero or unacceptable, right? You know what I mean? You still have to test, but,
Sure.
very, very high that. And the problem is if you deep dive into what people are doing right now, it's hard to yield 100 qubit chips. And you look at, the Google, for example, the latest chips, they have dropouts, 3-4 dropouts in the chip. And I'm sure they work hard, to find the good chip. So, even now it's, a few percent. How are you going to make a 1,000,000 qubit quantum computer? So we are working, with the semiconductor industry. Really, one of the big things is yield. And how do we make these devices so that we can have a high yield? And we think this is absolutely essential and critical because, it's hard to test our devices. We have to cool them down. It takes days. It's not like you put it in a wafer prober and you're done. So this is one of the reasons we want to go to a semiconductor manufacturer, is that the degree of precision and defect-free, production they could do is so beyond anything you've done in industry. Even if you build your own, your own processing unit for superconducting devices, you want to go into these modern tools where they put it in the cassettes and they do everything properly. This is, for me, is absolutely essential. We will not be able to build a quantum computer in a practical, cost-effective way until we use this technology. Now, what happens is, as soon as you start doing it in this way, you can't play the little tricks that they play and the physicists are playing. So you have to kind of reinvent every step. And this is what's hard. And, our job in Qolab is to get that to happen before we run out of money as a startup company. Okay. But I'm sure we'll get this to work. We're making really good progress.
I have full faith. The right people are involved. You got Alan and yourself. So how does that number then, evolve towards 1,000,000 qubits?
So what we plan to do is wafer scale, 300 millimeter wafer or so, and that's about 20,000 qubits. And then that's a module, which would have all the connections into room temperature and then you just stack and tile these devices together. And if you have them stacked up against each other, they can couple to each other. There's also ways to connect them, with maybe a flex wire or some other kind of a structure like that. People have kind of demonstrated, or for example, Rigetti has demonstrated that you could tile things together. They're tiling 9 qubit chips, okay, and which is great that they're able to show that. But I think you can do the same for cell arches. Not easy, but I think that's a way that you can do it.
Yeah. This is going to be an interesting one for you. Is when you reread the 2019 Sycamore supremacy paper today, with 5 more years of classical spoofing progress, what is the single sentence in it you would now edit?
Oh God. I haven't gone back and
You haven't gone back and reread?
no, because I spent so much time on it. I know it. I know it well. I was very happy. I would say that paper kind of represented the culmination of my career, in terms of doing an experiment. And we tried to write the paper so that people could understand it. And I wanted even high school students to be able to read, of course, there's a lot of stuff they won't understand. They get the essence. So we worked really hard. In fact, there was a kind of a battle at the time that the theorists wanted to put in phrases and sentences, paragraphs to make things define better. And it was like, no, let's not do that, because we want to make this really readable. And we had a supplement material where you could be really precise. It's 50 pages. And, so I really tried to do it. And I was very happy that it's I think, pretty readable. And I've had many people come up and say that they enjoy reading the paper and they understood and the like. Now, the interesting thing about the paper is everyone, it's like, okay, you've done this powerful computation and the like. And that was a big part of it. You've done a calculation that a supercomputer can't do. Now, of course, that's been broken since then but it's taken years. It wasn't broken in a week. Okay, that's what's good. And then people have done more complicated things, so they've done that. So that's what everyone remembers about it. But for me, and I have specific sentences in there, and most people have totally ignored, is what's important is that when we measure what the errors of the individual qubits or 2 qubits, the logic gates, we know what the errors are. You take those errors and then you use high school probability statistics on errors. You can then predict the error of the whole quantum processor. And then when we measure the error of the whole quantum processor, and they agree. And to me, the fact that quantum mechanics in a quantum computer, the computation's very complicated, but the errors are kind of classical.
Yes.
And just probabilistic. That's an amazing thing. And that is, I think, one of the bigger long-term demonstrations of that is that quantum mechanics works in this way. You expect it to work in that way, but practically it works in that way. And that's the one thing I wish people would, reread. Other people would reread and check out that sentence or two where we talk about that, because that to me is important. And that's maybe because I'm an experimentalist and I have to show that things work. But I think that's as important as the supremacy part of it.
Marvelous. Yeah. Dr. John, this has been a marvelous discussion. It could go even longer if I wanted it, but I want to get a little bit personal, on your side. So, since December, right? It's not that long ago. It was only 4 months ago. Has the Nobel changed which of your opinions people are finally ready to take seriously, and which ones the industry still is not ready to hear?
So, what has been astounding, as having a startup company, is it's a lot easier to raise funds.
The credibility is there.
Yeah, and of course, and I call that the celebrity endorsement. That's more important than your confidence. Okay, and what's funny is what we're trying to do. What happens in quantum computing is people say, oh, I have this magic qubit thing, and then, you give us money and we'll build a quantum computer in a short amount of time and whatever. And, I understand the appeal of that, and, maybe people will come up with good ideas, but I think in a sense there's a lot of hype. Right. And what we do is we say superconducting qubits are working really well, but to really get this, we have to solve this technical problem, which is fab.
Right.
Okay. And of course, that's expensive. And that's a harder sell. Now, there are people who understand that and will fund us, and they have funded us, and that's really great. But that's the problem here is we're not hyping up our technology. We're saying what we really have to do to get it to work. And that makes it harder But again, with the Nobel Prize, I think people can, trust our opinion a little bit more. And, that has made it easier. That's probably the biggest thing being evolved. The other thing, of course, is not in general, but when you go to a physics conference, a lot of students come up and they want to have a selfie.
The selfie.
which
It's nice.
which is very charming. Well, what I would say is if you were a Hollywood celebrity and that happened on the street, you would get tired of that really fast. I find it charming, but it's not all the time, right? So then it's okay.
I think the smart folks will know who you are. That's the difference, right? Is there anybody who will come up?
But I like, especially what people are very kind about is said they've read the papers, it's very clear. They've liked, the way we've done the experiments. I really appreciate that because a lot of times it takes a lot of extra effort and it's sometimes hard to do that. And when people show their appreciation, it's kind of like all worth it then.
What is the physics problem, not engineering, the physics problem that still generally keeps you up at night?
And
then I'll be specific on the path to fault tolerance.
Well, I'm just going to say that the materials physics of what's giving us this energy loss and what are the detailed models and how do you correlate what we're measuring with something, on our fab process and like it's very much, materials physics related. The way I like to say that glibly is that, I know how to integrate the Schrödinger equation. I know how quantum physics works. It's all the dirt physics that, keeps me up at night. And in particular, it's the materials physics that we really try to focus on and solve. And, that's what our company is trying to solve.
So before December, and I'm sure you've looked at the numbers and the statistics, your most cited paper was the 2019 supremacy result. So after December, it is the 1985 work.
That's we decided now. I haven't looked at my citation.
So after December,
that's great.
It is the 1985.
Okay. Well, yeah. Well, I'm glad people are going back and repeating it. And
isn't that crazy?
Yeah. And that was at the time that was we really worked hard writing that proper. That was a nice paper.
Yeah.
And I remember I went to France to visit Michel, and we sat together and talked for a long time. How to write the paper, and particularly we spent a long time on the first sentence. Okay.
Wow.
Do macroscopic variables obey quantum mechanics?
What?
That first sentence. And normally when I give lectures, I tell the students, never, ever start your paper. Recently, there has been much interest in blah, 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 because you don't do science because your neighbor's doing it or whatever. You do it because you're trying to answer a question. And you can't always write a direct question as your first sentence, but if you can, then you should do it. That's what I learned in writing that paper from Michel.
Wow.
It was really nice.
And then, the other key one is, which is interesting as well from the research my team's there. So in 1985, of course, you were working on, macroscopic quantum tunneling, a result that no one thought would matter commercially.
Oh, yeah, absolutely.
And now
very basic physics.
Very basic. And like 40 years later, it's a Nobel Prize foundational work. What would you say is the 2026 equivalent? As in the paper being right now that will matter in, I don't know, 2065?
Well, I'm hoping that the quantum supremacy experiment, change the field in some way. Show that a quantum computer can powerful, and then easier for people to raise money, and then opened up all these other people to do these things. It proved something there, and the only way I could tell that is after that paper, I got selfie requests. That's how you know. That's how you know. No, and I was like totally surprised. And then of course it's much more now. But I'm gonna say, recently, the QERA results on the atom traps, and then there's even just last week or so there was a paper by uh, Caltech. They formed a new company. I've forgotten the name right now, and also on how you might be able to make a smaller quantum computer and break elliptic codes. And also there's a Google paper on breaking internet security.
Yes.
And I think those are going to be important papers, not necessarily for quantum, but to get people in the security business, which is like, enormous, to take seriously the threats that future quantum computer might be able to break that. And then, it's time to get busy and to fix these things. And I totally agree. And the Google paper is great about that, laying it out. And I think people should really be taking this seriously.
Well, I mean, I think I can't remember where I saw you talking, and you said some serious statement about Bitcoin.
Yeah. Yeah, well, that's right, and
you generally
I don't. It's in that paper,
yeah.
But people in that community has to read that paper and really thinking carefully about what they're doing, and they're the experts. I'm not the experts. What I say is the possibility of these quantum computers being built in some amount of time. I think it's going to take longer. I'm a realist, but it's looking like it might really be possible to do that. I mean, we're trying to build digital systems, and we think we have a good way to do it. Other people are claiming the same thing.
Right.
People need to take that seriously. And I would say the talks we heard yesterday is all consistent with the idea that this might be happening sooner rather than later.
And that is the first thing from a use case. I mean, it's encrypted.
It's actually the easy the Bitcoin, which is elliptic curve codes, is like the easiest thing to break that we know of. The easiest algorithm that's practical. Okay, I hope that my field just doesn't break things. But it's what it is, and I think people just need to pay attention. And again, the Google paper is great.
Yeah.
They'll talk about that. You see what the numbers are, and these kind of time frames I think are reasonable. And for example, I say 5 to 10 years. Sundar Pichai says 3 to 5. Okay, but he's a CEO of a big company. He has to be sooner rather than later. So our numbers I think are kind of compatible, and certainly Google, the theory team understands this really well. So, it's something people to think about in the.
Is there anything that people can do to protect that, or is that?
Well, I'm not an expert, so I don't, I don't want to comment on it, and I'm sure it's a subtle issue, but I guess again, there's papers out there you can judge for yourself, and the only thing I understand of reading the Google paper is that the Bitcoin community is kind of ungoverned, if you want to say, and of course, then it's going to be hard to decide you have to do something, right? Okay.
My concern for that is that the government treasury, all that money that's being stored by the government.
Yeah.
Crypto.
Well, no, and I think the other thing is if it's unclaimed Bitcoin, the government can claim it, but also bad actors, terrorist organizations, mafia organizations, whatever, can claim that, and it's a huge amount of money. So, again, it's a serious issue. And I know Alan Ho has been he talked to people in Treasury about that,
right?
A while ago to let them know that this was coming.
Yeah.
So,
to wrap things up, I mean, I'd love to have you again and have. I want to. Right, it's right. It's really a discussion, and then the thing is the next time I'd love that is both yourself and Alex.
Yes.
In
We have a good team.
Yeah, that's gonna.
That's what I like about working with Alan is we kind of complement each other, but we can see, and it's this is what we learned at Google. Is one of the reasons Google was successful is the founders were a really good team together and complemented each other. So
to wrap things up, 10 years from now, is Qolab a component supplier to IBM, Google, or sovereign of the day, or a vertically integrated company shipping full quantum systems?
Maybe both. So, what we think of is we think of ourselves, we just creating valuable technology, and then we'll just see what the market does as determined with our business plan. Frankly, I'd love to build a quantum computer. That's what I joined Google, and I love that. But if we just have to build the essential chips and to figure out how to do that properly, I'm totally happy with that. It's just, I want, and in fact, I'll be happy if someone builds a quantum computer, right? And, being part of the whole infrastructure to encourage having people build this and bring this technology. That to me is success too.
But which ending is the one you are?
Oh, I want to build a quantum computer.
Let's go.
The whole thing. And of course, we'll collaborate. But I would like to build the whole thing. But I understand we're a little company, we're behind everything. But little companies have won out in the end. It's possible. And I think if you can build the chips and manufacture them better and less costly, that's a huge advantage.
Dr. John Martinis, thank you so much for this wonderful discussion.
Thank you.
Is there anything that you'd like to tell the community or anybody out there? Is there any message you want to hand out? Or
just that it's an exciting time. You should keep monitoring what's going on. There's a lot going on in the field now. I have it hard the time to keep track with what's going on.
Yes.
But it's very exciting.
Very exciting times. Ladies and gentlemen, thank you for tuning in to the Semiconductor Leadership Podcast episode with Dr. John Martinis. If you guys are interested in Qolab, you can check out their website right here. Click on the link, it will pop up. Visit them and educate yourself about them. If you're an investor, invest in them. I mean, I hope they do. I like that. I hope this episode showed you exactly how incredible the work that they're doing. And yes, as they say, it takes a village to raise a chip, and also it takes a village to raise a podcast. So hit that subscribe button, and if you enjoyed it, like it, share it, and also give us a comment below on what you liked about the discussion. Until then, take care and see you at the next episode. Bye for now.